Have quantum computers just got 10 times closer to breaking encryption? There is a paper that came out recently which has created lots of discussion about whether we've just become much closer to breaking encryption with quantum computers. And it's this one here, which is about reducing the cost of breaking RSA 2048 to 100,000 physical qubits using quantum LDPC codes. In this video, I want to explain a bit about what the background is to these kind of estimates about how close quantum computers are to breaking cryptography, how that's been evolving over the years, and what my reaction is and the kind of community reaction is to this new estimate and what it means for getting closer towards breaking cryptography. So if you're new to my videos, I'm Maria Villaris. My background is in the foundations of quantum information. I did my PhD at Oxford, and then I started working in the quantum industry, which I've been working for some time as well in quantum computing. And I also make videos like these in my spare time. So to give a bit of background for people more new to quantum computing, we have quantum computers being built at the moment. They already exist. They're based on quantum bits, qubits, instead of classical bits. And for certain problems, they are much faster than classical computers. But the quantum computers that exist at the moment aren't yet big enough and have errors low enough to achieve those useful computations faster than classical computers. Now, one of the problems which has drawn the most attention to quantum computing historically is to break encryption. So there was a scientist, Peter Shor, who came up with Shor's algorithm, which is an algorithm for using a quantum computer to efficiently find the prime factors of a number. The difficulty of factorizing is the basis of a lot of our cybersecurity, in particular using this technique known as RSA encryption. And so this is the basis of the cybersecurity that is most of what we use in our day-to-day life, our banks and many different things around us. Society as a whole is trying to transition to a different set of ways to do encryption known as post-quantum cryptography. So the idea of this is that these types of encryption are resistant to attacks from quantum computers, and there's become a idea in the quantum computing space of Q-day, the day that a quantum computer is able to break encryption. We need to shift to post-quantum cryptography before this Q-day happens. And so a big question in society is, when is Q-day going to happen? And historically, there have been a range of estimates for how good a quantum computer do we need to run Shor's algorithm, reaching this Q-day. An important idea that's going to be useful to understand what this latest development is and what these resource estimates really mean is quantum error correction. Quantum computers are based on qubits, which are very fragile, so they suffer lots of errors due to interactions with the environment. And it's well known that to reach very low errors in a quantum computer to the level that's needed to do useful applications, we're going to need to do a kind of smart trick called quantum error correction, where you essentially take lots of these noisy qubits which have errors and encode kind of one clean low error qubit using all of these noisy qubits. So these noisy ones are called physical qubits, and then you encode what's called a logical qubit, and you can use different types of codes to encode these logical qubits, each having different properties, and that's going to affect how you structure the architecture of your quantum computer. The kind of default strategy for doing this process of error correction for some years has been based on something called the surface code. And in 2012, there was this nice and famous paper from a group of researchers presenting the idea of the surface code architecture, this way of doing quantum error correction. They also did a kind of back of the envelope estimate of the resources needed to run Shor's algorithm. And at that time in 2012, the rough estimate was that it would need about 1 billion qubits to run, and that would be in a realistic timescale of, say, days. Interestingly, since then, that figure has been getting smaller and smaller and smaller. In 2019, there was a new estimate that you can run Shor's algorithm with 20 million noisy qubits in 8 hours. If you look at this paper, the assumptions that it's based on are those of the kind of approach to quantum computing that Google are taking. And so in quantum computing, there's lots of different ways that you can actually build a quantum computer. One of the most popular ones is using superconductors, and this is the approach taken by the kind of big tech companies as well as various startups. There are also other ways of building quantum computers, for example, using ions, atoms, photons. So the timescales, like the 8 hours, the number of qubits, these are very closely tied to what assumptions you make about the hardware. But because it's with this kind of surface code approach and with this superconducting hardware in mind, it is kind of comparable to this billion-qubit rough estimate that was made in 2012. So it's a kind of like for like, in a sense, reduction from 1 billion to 20 million qubits. Okay, so that was in 2019, but now is 2026, and a new estimate was put out in 2025 by one of the researchers of this paper, Craig Gidney, because since 2019, lots of development has happened in quantum computing. In particular, there are 3 significant developments which happened between 2019 and 2025 that affect the estimate for Shor's algorithm. I think people kept asking Craig Gidney kind of what the implications of these new developments were for Shor's algorithm. He did a kind of new estimate of the resources needed to break it using the same kind of assumptions as the 2019 paper about the properties of the hardware, but with these kind of new developments in mind. So one of them was a development in the algorithm itself, so reducing the resources that you need to run the algorithm by finding a better way to run the algorithm. So that's this first development that's mentioned, using approximate residue arithmetic, a kind of algorithmic improvement. The second is a development called using yoked surface codes, and the idea is that a lot of the qubits of a computation in a quantum computer, when running Shor's algorithm, are idle, doing nothing, waiting to be used when they're needed. And this yoked surface code approach is a way of essentially being able to encode these qubits that aren't doing anything more densely. And the third one is a technique called magic state cultivation. In the past, people thought that the kind of biggest dominating overhead of quantum computing would be a process called magic state distillation, which is to do with creating magic states. If you don't have any magic states, then you could simulate a quantum computation fully efficiently with a classical computer. So magic states are kind of required to have the acceleration that comes for using a quantum computer for certain problems. This magic state cultivation approach provides a way of creating these magic states without much more overhead than other states. So combining these developments led to a new estimate of less than 1 million noisy qubits needed in 2025. So that's down 20 times from 20 million. Note that the previous estimate had 8 hours in the title, whereas this estimate does not mention a timescale in the title. And the actual timescale is less than a week in this paper, so it's longer than the 8 hours, so there's a kind of trade-off there. We now have this new paper saying that the cost is reduced to 100,000 physical qubits instead of the previous estimate of 1 million. It might seem that progress has suddenly kind of rapidly happened because we've gone from 20 million in 2019 to 1 million in 2025, which seemed like a big jump of 20 times. But then we've gone like another 10 times lower in a year. I think there's a lot of subtleties in actually understanding what this paper is saying, and it's not actually a like-for-like comparison in terms of the resources needed to run Shor's algorithm to these previous set of papers. So in this kind of run of papers, they were based on the assumptions of using this surface code architecture inspired by superconducting quantum architectures. And so the error rate was kind of assumed to be this 0.1%, which is kind of seen as the realistic error rate to say for superconducting qubits. Another aspect is how fast the operations are. They're about 1,000 times faster on superconducting qubits than ions in atoms, so that makes a big difference. And another assumption is to do with the connectivity of the qubits. So in superconducting hardware, the qubits can only interact with the qubits that they're neighbours with. But with some other architectures, like those based on ions in atoms, you can have something called all-to-all connectivity, where any qubit can be made to interact with any other qubit directly. That opens up a different set of ways that you can do quantum error correction that are different from this surface code approach. So what's being shown in this paper is the approach of using quantum LDPC codes. Quantum LDPC codes, or QLDPC codes, have become more popular in the last few years because what they enable you to do is encode more logical qubits per physical qubit in your quantum computer. But it has more constraints on the hardware. So one of the reasons the surface code is really nice is because it works with this local connectivity, whereas these QLDPC codes require more connectivity. And so they are possible on the architectures that enable connectivity between qubits that are far apart. These QLDPC codes could be implemented on ions and atoms. They can also be implemented on superconducting hardware, but they need specialized engineering which hasn't been performed yet in order to enable that kind of connectivity. So companies like IBM, for example, have a roadmap based on some QLDPC codes that they have developed and are promising for quantum computing, and they're engineering their architecture in order to have these kind of extra connections between qubits that are far away from each other. There are trade-offs that come with that, not just with the engineering needed to develop novel architecture, but there are also other trade-offs. So the surface code has really nice ways of doing logical operations, so computing on your logical qubits. There's nice ways of doing decoding. So this is a process where you're figuring out what errors happened in your logical qubits, and this needs to happen very quickly. You need very fast decoding to kind of keep up with your computation. Okay, so what's happening in this paper? Well, they present an architecture for using QLDPC codes, which is a pretty cool paper, because you might say, oh look, with this code I can encode more logical qubits per physical qubit, but to really demonstrate what that means in practice, you do have to dig deep into the details of how you're actually going to implement the different aspects needed for the quantum computation. And what they do in this paper is present an architecture and a resource estimate of how all those pieces work together. They're also introducing new techniques so that these QLDPC codes are made particularly efficient in this context. So if you look through this paper, they kind of present this modular architecture. And so what they find when doing an estimate of the number of qubits needed to run Shor's algorithm with this architecture is that it is around 100,000 physical qubits. One reason this isn't like for like with the other estimates is that it's based on this different type of code which actually needs different engineering to work on certain platforms. They have tried to keep lots of the assumptions similar to the previous estimates. For example, keeping the error rate of 10 to the minus 3, so that's 1 in 1,000, 0.1%, and the kind of timescales for running the operations. One of the challenges for QLDPC codes is actually being able to sustain reaction times that are this fast. There hasn't yet been kind of generally found methods of doing this fast decoding, so that's a limiting factor in how fast they are able to run, which isn't accounted for in this estimate. I thought it would be useful to look at a table that they have in this paper, which kind of shows you how different trade-offs come into play. So this kind of code cycle time of 1 microsecond is so that's like 1 in a million. That's the kind of usual superconducting, and you can see that this under 100,000 qubit estimate actually takes a month to run. You can get it to under a week with 150,000 qubits, which is still a lot less than a million. If you want to do it on a superconducting platform, then you have to create new engineering. So that's the caveat with that option. And then if you go to the other side, currently the kind of timescales of ions and atoms are more like 1 millisecond, so they're kind of on this side of the table. With ions, there are kind of examples where you can get the error rate down to 10 to the minus 4, so that's a really low physical error rate of like 1 in 10,000, which is really cool. But it does mean that if you want to have a month runtime, you already need 3 million qubits. If you want less than a week, you need 14 million qubits. You're in the kind of millions now, rather than in the hundreds of thousands. It's not as simple as just looking at the qubit number and seeing which one can do it with less qubit number and less time. There's much more to it than that. But I think this table does help see that, at least with the platforms that are out there right now, there isn't kind of one that gives you everything. Like, if you're going to use these novel codes, then you're going to have to compromise on having to do new engineering, or compromise on time, or compromise on the number of qubits you need to use, or you don't bother trying to use one of these novel codes. Instead, you use something like the surface code, just kind of add more and more qubits if you can scale that up to the levels needed to do useful quantum computing. Using these kind of novel types of codes isn't the only way to reduce the estimate of the number of qubits you need to run Shor's algorithm. So there are other estimates that have been done. For example, this one from 2021 with only 13,436 qubits. It comes at the cost of a new hardware innovation that hasn't been done yet. A technique for building hardware where you can essentially use many modes of a single system to encode information. Similarly, there's another estimate. This one is based on a different type of encryption, elliptic curve logarithm. This is based on a different type of hardware called using cat qubits. So these are qubits that have a particular type of noise. And this was in 2023 and kind of had a similar magnitude estimate to this recent one of 126,133 cat qubits. It does require a significant new challenge to the hardware of building these cat qubits. So to step back a bit, what does this mean for how close we are to breaking cryptography, and has Q-Day become closer? I think that these two estimates that kind of used the same hardware parameters in 2019 and 2025 show you that we have got closer to Q-Day, so we've been getting closer on the hardware side to having good enough hardware to implement this, and then lower on the resource requirement side so that they're getting closer and closer to meeting. And something interesting which happened last year is that we started seeing company roadmaps from the quantum industry actually having devices that are able to run these kind of cryptographically relevant algorithms with years where they're aimed to be developed. So for example, the company I work for in my day job is Oxford Quantum Circuits, which is a superconducting quantum computing company spun out from the University of Oxford. And this is the roadmap that we put out last year. This 2034 device is aimed to be this cryptographically relevant quantum computer. You can see one of the applications here is decryption, and the actual paper that's linked here is this paper from last year. So to summarize, I would say that we have not just got 10 times closer to breaking encryption. This paper is providing new contributions to enabling you to use this type of code to do a quantum computation in a reasonable amount of time, which is really cool. So exciting research, and we'll see what more estimates of Shor's algorithm appear in the next few years.